So hello everyone. As Dhruv said, my name is Mohammad. I've just earned my PhD in civil and environmental engineering at the University of South Carolina. And during this internship, I've got this privilege to work with Dr. Dhruv Balwada on the project entitled Decomposing Sea Surface Heights into the contributions from different physical processes using machine learning. So looking at the oceans from space is a good way to learn about them. Satellites data can cover large areas and track changes over time. What we can directly observe from satellites include sea level, temperature, and colors. But there are some other desired variables such as ocean currents, which we cannot observe directly. Ocean currents are crucial components of the Earth system and play an important role in transferring heats, momentum, and tracing gas between oceans and atmosphere. This precious component can be derived from corresponding sea levels. For current generation of satellites, which have spatial resolutions between 50 to 100 kilometers, the ocean currents can be estimated simply by taking the spatial gradients of the SSH or sea surface heights. Recently, SWOT has been launched and added to altimeter's constellations for measurements of the Earth's water surface elevations. SWOT will observe the SSH over 120 kilometers wide swath with the spatial scales down to 15 to 30 kilometers. And at this spatial scale resolution, SWOT signals will contain both balanced motions and inertia gravity waves, including internal tides. And internal tides would have an imprint on both sea surface heights and the velocity fields. But what's the problem? I should notice that it's only balanced motions that have impact on long-range ocean transports. And if we want to use gradient relationship to drive ocean currents from sea surface heights, sea surface height should just include the balanced motions components. So in this project, we focused on decomposing the sea surface heights into two important components, including balanced motions and internal tides. As we want to use machine learning approach to do so, we used the products of a numerical model. Here in the left figure, we show the visual representation of the SSH taken from Agulhas region of the LLC 4320 simulation. And the middle and right figures show the visual representations of its two components, including balance motion and internal tides, respectively. This slide shows the power spectra of signal representation of the SSH and its two components in frequency domain. And we see the amplitude of each component plotted against its frequency. As it's evident, sea surface heights and balanced motions both have the same order of magnitude for low frequencies, or in the other word, large wave numbers, while for higher frequencies, their amplitudes deviated from each other. In the case of IT and for low frequency, the difference in amplitude is more than 4 orders of magnitudes, and it gets closer and closer as the frequency increases. And this is where we believe the role of internal tides become more important. So many different approaches have been adopted to address this problem. Two more common, which are ML-based, are as follows. In the first study, they try to filter out the tidal components. They use a ResNet architecture and test their model on eNatal 60 simulation. They also try to incorporate different independent variable like temperature. In another study, the authors used conditional GANs to extract internal tides. In this study, given the sea surface heights as inputs, the model were missioned to generate the IT components as a result. So accordingly, we took this two different approaches. For the same approach, we tried to filter out the tidal components using a simple linear model equipped with different loss functions, different types of loss functions. And in our second trial, we used conditional GANs to generate the desired internal tides given the sea surface heights as inputs. We used 70 days of SSH data of LLC 4320 simulations for a glass region. This region was selected because of the presence of strong mesoscale flow features. And for data transformations, we used min-max normalizations and then scaled the result to -1 to +1. For our first approach, we adopted a simple 5-layer CNN followed by a parametric ReLU activation functions. Just for the head activation function, we consider tan H to map the logits back to -1 to +1 to be in accordance with our data transformation. In addition to mean square error loss, we added first order and second order derivatives as auxiliary loss function to alleviate the blurry effect of mean square error loss functions and help sharpen the predictions. This slide shows a visual representations of how first order and second order derivatives emphasize on high frequency information. For the first order derivative, we used Prewitt kernels. And for second order derivative, we use Laplacian's kernel. And according to our experiments, we noticed that isotropic form, which is the right one, performed better than the simple one. Again, here we have the power spectra of signal representations of the balance motion, and this balance motion is for specific regions that I showed here. And first order and second order derivatives of balance motions in frequency domain. They could have a positive, as you can see here, they could have a positive effect on training by regulating the amplitudes of the components from low to high frequency. This plot shows the results of the model on frequency domain for all 7 days of existing in validation set. The orange line show the base model, which just use mean square error loss function. This model cannot catch the low frequency component, but we can see in green line and red lines, which are related to the models with auxiliary losses, we show that how first order and second order derivatives can improve the results. And we can see on the bottom left of the canvas, the metrics on the spatial domain also approve what is presented in frequency domain. So when the results of these models that I showed in the previous slide were used to drive the corresponding IT component according to the top right formula, the output will not be promising at all. This result imply that such a simple architecture could not generate satisfying IT components, regardless how many hand engineering loss functions we incorporate in the training procedure. But one cool thing is in high frequency, which if you remember the first image on frequency domain, we compare balanced motions, SSH, and internal tides. When we have a comparable internal tide components, we can see here that the model could catch in this part. Keep this take-home message. We use for our second mission, we use the conditional GANs to extract internal tide components. In addition to loss function determined by the discriminator, we use L1 loss to separately evaluate the performance of the generator by comparing the generated ITs with the real ITs. Yeah, this is the code from the papers that we use in this for these experiments. As a community, we no longer hand engineering our mapping functions, which means that we use, for example, MLPs or CNNs to automatically learn the mapping functions. But in this paper, they claim that with this work, they suggest that they can achieve reasonable results without hand engineering our loss functions. And I believe this is what LEAP is all about, learning the Earth system with physics and machine learning. And here we totally rely on machine learning to see what would be the results. For this model, we train our model in 4 different configurations. For the baseline, the model was trained for 200 epochs. And for the first variants, the trained model was fine-tuned for another 100 epochs using mean square error plus first order and second order derivatives loss. And in the third variants, the trained model was fine-tuned for 50 epochs using mean square error loss functions on both spatial and frequency domain. And as a third variant, the model was trained for 500 epochs from scratch. Again, this plot shows the results of the second approach on frequency domain for all 7 days existing in validation sets, because it's so messy having all of these things together. Let's go through each model separately. This is for the base model. Model performed good for low frequencies, but it overestimates high frequency components. This could be because we didn't include the coastal area in our training. In these regions, ITs have a high frequency component, which is ignored during training. The other problem is the noise spikes, as it's obvious, but it was expectable because during the inference, we did the inference somehow has been done on 256 by 256 patches, and then these patches used to retrieve the whole 2048 by 2048 canvas. So these spikes could be appeared on the border of the patches when they get merged together. This plot shows the result for first variants. This model used other types of loss functions compared with the base model, and it seems these auxiliary loss were able to take care of the noise spike and the overestimations during on the high frequency components. But you can see it get somehow deviated for these parts. We see almost the same situation for the second variants. Mean square loss on frequency was able to attenuate the noise spike and overestimations of high frequency components. Yeah, this is the last variant, which has the better situation regarding the noise spike. It also performed better for high frequency components. Regarding the spike, using different padding strategy, we may be able to alleviate the situation. Right now, we use reflective mode. And for high frequency parts, we may need to use weighted loss or some other customized loss, considering different loss for low frequencies, like the loss functions that I drive on top right. We have 2 different conditions for different frequency components, and also we should include somehow coastal regions in the training part. This is the visual representations of the grand truths on the whole canvas and what we generated on the model. As I explained and as I emphasize, we exclude the region, the coastal region. These 5 canvas on the right, on the bottom right, so we can see model we're not able to capture those things and generate those components appropriately. But for the other parts, for other regions, we got a very impressive results. For example, here we can see the model capture and generates all of the components, and also regard the visual representations is so good, and also capture all of the heights as they really are. Even if we zoom more, we can see how beautifully the generated model were able to produce the IT components. And this is for another region, which the IT got distorted, completely distorted. Still, the generated model were able to decently reproduce the components. As a conclusion, I would say we assess just the skill of machine learning for decomposing sea surface heights components, and we figure out that extracting ITs seems to be more challenging, and for high frequency and high frequency components is harder to capture and generate. For future works, we could investigate on different loss functions and make our models stronger regarding the low frequencies, and also investigating on different model architectures. I'm so optimistic about diffusion models because they seem so fit for such a problem. There are two challenges for diffusion models. First, they usually not always, but they usually norm Gaussian noise. But here we should change this specific type of noise, which is so compatible with machine learning architectures with internal tides component. And the other thing is this noise get added to the inputs over time, and in a Markovian chain approach. But what we should do, we should change it to instead of using time domain, we should use it in the space domain. What I mean the model should learn, for example, if we feed this component as a first component, so the second component is not going to be along the time but along the space. Let's say after this component we could add this component, and then ask the model understand how the noise changed along the space instead of along the time. So I guess that would be so interesting to investigate. And the other thing is surrogating machine learning for other purposes. On the right side, you can see the figure of the all altimeters constellations for the ocean, and you can see there are a lot of white space which we should fill the gap before we do analysis. I believe we could also surrogate machine learnings to generate and somehow, let's say, interpolate what is happening in between. In computer vision, we call it image in painting, with which right now we have a very promising result and promising models. I'm done here. Thank you so much to listening to me, and I should also thank Dhruv Balwada, who was my advisor in this program, but from now on he's going to be one of my friends. And if I want to say something for him, the only thing that I found surpass his knowledge is his decency and his character. Thank you so much for listening to me.
Thank you, Mohammad. That's very nice. Now we have some time for questions. So you can raise your hand. Yeah, Pierre, go ahead.
Yeah, great. First of all, I have to say I'm very impressed by everything I've seen so far. And I would say it's not your fault, but it's pretty dense for us to grasp. So maybe that's also why we don't have so many questions, because you achieved a lot in such a short time. So that's really, really impressive. I was wondering, in a sense, everything is kind of multi-scale here, right? So is this why you're thinking of diffusion models, or as opposed to convolutions? Because convolutions, you could say, I mean, they have some multi-scale property, but you would want to impose like some structure into that, so just curious, about your thoughts on that.
By saying diffusion here, I mean the procedure of the diffusion, which we add the noises to the inputs and then ask the model, and regardless what type of model we use, and CNN could be included there to learn this noise. But the problem with conventional diffusion model is these noises are added over the time. But for our problem, first, the noises are different. If we assume internal tides as noises, then this noise is not as simple as Gaussian noise. And the other thing is the Gaussian noise amplified over the time, we should change it over the space. And I guess it's a very good, interesting topic to investigate, to see how models can learn ITs as a noise in different in different place in the spatial domain. But to answer your question, we could use any type of models to learn this pattern. It could be CNNs, it could be hybrid CNNs and transformers, or other types of models. Somehow the diffusion gonna act like data augmentation here.
Great. And maybe just a clarification, I mean, for diffusion models, I mean, time is an abstraction, it's not real time. So
exactly, yeah, thank you.
Space, right, that's okay,
Yeah, exactly. Yeah, thank you for noticing. Yeah, I should clear that. Thank you, Pierre. By saying time here, it's not a real time domain in our problem. We mean the each step which we add or amplify the noise, we consider that a step as a time. But yeah, you're right. I should clarify that. Thank you.
Thanks so much. Yeah.
All right, if nobody else has any other questions, I'm sure Mohammad will be available if you think of a question later on our Leap Slack channel to answer it. But otherwise, let's thank both our speakers again. Yeah, it's been a very great experience working with Mohammad, and I'm sure Kara's had the same experience with Matt. Yeah, and thank you everyone for coming.